and lambda 1 of f is greater than 1, then f is Salem or quadratic. Today we prove another theorem. So X surface F is a birational automorphism. Lambda 1 of F is greater than 1. Oh, sorry, here is lambda 1. Then lambda 1 of F is inside U, which is union of Salem and Pizzo numbers.
And lambda 1 is something that you called D1.
Yes, sorry, yes. I'm going to call it D1. I just am used to this notation and it is difficult for me to, yeah, but I will try. If dynamical degree is greater than 1, then it is Salem or Pizzo number. So let us prove this theorem. So the first step in the proof is the following fact. Theorem. So probably I should say here that this theorem was proved by Diller and Favre. So this probably we can attribute to Kanta, but this is rather easy assertion. Theorem also by Diller and Favre, which says that a birational automorphism of a surface can be birationally conjugated to another birational automorphism, but with nice property. So X surface, F is a birational automorphism. Then there exists a birational morphism, so a regular algebraic morphism from Y to X, which is just a sequence of composition of several blow-ups of points, such that so we have Y, we have X, here we have our birational automorphism F, here is delta. Here we get another birational automorphism, just F defines G. G is birational, but it has the following property. The action of iterate of pullback on Neron-Severi group coincides with the action of the pullback of iterate. Birational automorphisms with this property are called algebraically stable. Algebraically stable, I'm going to call them just AS. So this is the notation. It is easy to see that any regular automorphism has this property. And in fact, we last time we had an example of a birational automorphism, which also has this property. So let me.
We say that for some f there is delta and g, some that g is algebraic stable.
So there exists such composition of blow-ups, such that the induced birational automorphism on the blow-up has this property.
Sorry, could you remind what is the difference between Neurons-Severi group and the first Chow group.
So Neurons-Severi group by definition is Picard modulo pic 0.
Okay, so to use this definition, we need to introduce topology on. No.
So
0 means degree 0.
Yes.
Okay.
So if you like, instead of Neurons-Severi group, you can think about H11 of Y, just the middle Hodge cohomology.
Okay.
So and all the results will be the same.
It's better to cancel out because sometimes this Neurons-Severi still have some portion.
Okay, yeah, sometimes.
You are considering the induced operation on the vector space, so usually
Okay, R.
So anyway, Chow group is something modulo rational equivalence, and Neurons-Severi group is something modulo numerical equivalence. So it's much more
Smaller. Yeah.
So alternatively, we can say that modulo the kernel of the intersection form.
Modulo numerical equivalence.
Okay. Yes.
But there is some theorems about regularization, so it's something like that you can lift and have some regular math. What is the difference? I'm not sure, maybe
Yes.
you don't have some theorems. But
So let me just give you an example, the yesterday's example. We had birational automorphism of P2 defined on A2. XY goes to Y X plus Q of Y. And degree of Q is greater than 1, strictly greater. What is so Neurons-Severi group of P2 is just Z. Oh, sorry, NS of P2 to NS of P2. It is just multiplication, so D equals degree of Q. It is multiplication by D. And when we replace it, when we consider the iterate Fn to power pullback, then it is just multiplication by D to power n. So it is exactly, so we just checked that the degree of this polynomial, the second polynomial in, so there was lemma, that Fn of xy equals P1 of xy, P2 of xy, and degree of P2 equals D to power n. So it defines an automorphism of degree D to power n. And we just get that these two birational automorphisms are equal. But you can observe that the dynamical degree of this birational automorphism, it equals D. It is an integer. So it is not a Salem number. And we know that if we have a regular automorphism, then its dynamical degree is a Salem number. So this birational automorphism is non-regularizable. In any case, we can construct an algebraically stable model, but the regularization model sometimes don't exist. Yeah, and not a proof, but a comment how to prove this theorem. So, in fact, F is not algebraically stable only if we have the following situation. If we have some divisor E inside exceptional locus of F, so it maps to some point, probably then point maps to a point, and then this is a point of indeterminacy, and it maps to another curve by f. So these are images by f. If we have such situation, then we just can see that pullback of this curve by f is just 0, and pullback by f cube contains this curve. So in this case, f indeed does not satisfy this property. But if we blow up these points, then we get an algebraically stable automorphism. So it is the idea of proof. I don't want to tell more details.
Можете еще раз быстро повторить, какое у нас описание вот неалгебраически стабильного случая?
Это тот случай, когда у нас есть исключительный дивизор, такой, что его собственный образ лежит в множестве неопределенности какой-то степени fk. Вот. Ну, дальше можно проверить, что вот таких вот ситуаций будет, конечно, много, и мы можем просто раздуть эти точки. Okay, so we want to prove this theorem, and we just replace x and f by its algebraically stable model.
Excuse me, can you explain again where if f is not algebraically stable, then the image of exponential
In what? Why is this the problem? Because so pullback of this curve is 0 under f, and pullback under f cube is non-zero. So it lies in kernel of pullback by f and don't lie in the kernel of pullback of an iterate. So we replace x and f by y and g, and we further can assume that x f is algebraically stable. It is very useful because we want to compute lambda 1. So in this situation, just we get that lambda 1 of f is the spectral radius of the action of pullback.
You mean we can assume because we can take...
Yes, we just replace xf by this.
Sorry, what do we want to prove?
This theorem.
Okay.
The dynamical degree is safe
Yes.
when we replace.
Yes, yes, it is a birational invariant. So d1 of f is a spectral radius of the pullback. This is so the same linear algebra as on the previous lecture. Moreover, even if f is birational, f preserves the numerically effective cone. So it is convex cone of full dimension and closed. So by Perron-Frobenius theorem, we observe that d1 of f is just the greatest eigenvalue. We get that the greatest eigenvalue of action f on Néron-Sévère group is real. d1 of f is just greatest eigenvalue. of pullback. And so now our goal is to compare the greatest eigenvalue and other eigenvalues of f.
Where does this pull from?
This?
F star,
This? So you can just check. Yeah, it is just some fact from birational geometry.
Algebraic stable or?
No, it's just for any. It follows from the fact that X is a surface. For threefolds it is wrong, but on surfaces it is true.
And then in this case, which step do we use that is algebraically stable?
Only here. Here we use that it is algebraically stable, and for this conclusion we need just that it is. So we just reduce the question of growth of neuron Siveri group under the action of pullback to the question of spectral radius for just f without iterates.
Yeah. We have to compare the action of the iterate and the iteration of the action.
Yeah, and also what we can see from the fact that f is algebraically stable is that d1 of f, so it is spectral radius of action of f on neuron Siveri group. It preserves lattice, so it is an algebraic integer. And the degree of this integer is bounded by the Picard rank of x. Because d1 of f is eigenvalue of an integer matrix. Yes. So we just should show that all other eigenvalues of f star lie inside unit disk, inside the closure of unit disk. Unit. Because we want to. Yes, all other eigenvalues lie inside unit disk.
It's important to remember the definition of Salem number.
So all, yes, and Pizzo, yes.
No, in Salem and Pizzo, you have some number which is maybe large, and all its conjugates are much better. That's the definition of Salem.
Yeah, so, okay, I don't want to recall. So, in order to study other eigenvalues of action of pullback, we need the following lemma. So f is any not necessarily algebraically stable, just a birational automorphism of a surface. Alpha is just a class in any class in neuron Siveri group of X. Then push forward pullback of alpha equals alpha plus sum by exceptional divisors for the inverse map alpha intersected with E times E. So I don't want to prove this lemma, but so in fact you should check this equality just for blow-ups, which is easier. And then by strong factorization theorem, you will deduce the result. And corollary, so if alpha and beta are classes in neuron Siveri group, then we get, we can check that product of pullback of alpha, intersection form of pullback of alpha and pullback of beta equals alpha intersected with beta plus sum by exceptional locus of f minus 1 alpha intersected with E, beta intersected with E. Here we just. Why is question?
The problem. I know what what is d1? d1 is limit of x star h multiplied by
Yes.
r. And lambda 1, what is it?
It is the same. Sorry. It is d1. It is d1. It is just
But okay.
my consciousness.
But S and rho, it was Salema number.
Yes.
And they complex number.
It is a real number, lambda. So let me define u. Lambda is a real number greater than 1, strictly greater than 1.
What is an unit disk? Say something about
All other conjugates, all is conjugates. It's real is greater than 1, so it's outside unit disk. But all is conjugates.
Lambda 2, lambda s inside unit disk. Yes. Sorry. Sorry?
D1 bar.
But intersection form with another form on neuron spheric group. So let me define form Q of alpha beta. It is sum by all E inside exceptional locus of f minus 1 alpha E beta E. So space, and it is negative. Now, and beta are vectors for the inverse image. And as C of x, they are eigenvectors. So pullback of alpha equals lambda alpha, pullback of beta equals mu beta, lambda, and assume that lambda and mu are their absolute values are absolute value of lambda, absolute value of mu is strictly greater than 1. Let us use this formula. Absolute value of lambda times intersection form of alpha with alpha, it is just intersection form of pullback of alpha times pullback of alpha. But by this formula, this is alpha intersected with alpha plus q of alpha alpha. So we get that intersection form of alpha equals 1 over absolute value of lambda squared, minus 1 times q of alpha alpha. And by the same reason, alpha beta equals 1 over lambda mu bar minus 1 q of alpha beta.
Mm-hmm. So in corollary, how you prove it? You just apply this lemma for intersection formula with beta.
And use the projection formula, yes.
Yeah, and then projection formula. Okay, but if you apply beta on the right, shouldn't be in the sum alpha e and the next e beta?
But e beta equals beta e. It is symmetric.
If it's Hermitian formula, isn't should be conjugated?
I mean, so it is form like this. I mean, it is commutativity of. I mean, e is fixed. Just these are two places where we substitute something. This is form of alpha and beta.
So you mean okay? Q is just Hermitian. Okay.
Why is Hermitian form? Why do we speak about Hermitian form?
Because because alpha and beta could be complex. So alpha q defines symmetric bilinear form scalar product on neuron-Severi group.
Complex numbers and multiply the neuron-Severi group only by R instead of C. I think this will save all the difficulties with Hermitian form.
Sorry?
Couldn't we consider everything with real coefficients?
We can't because alpha could be complex. So we have eigenvectors.
A real matrix can have complex.
Yes. Okay. This is.
No doubt, but at least on the real space it will just the most.
Yes, on real space it.
Usual bilinear symmetric form.
Yes, bilinear symmetric, non-negative form. Yes, but okay, it is just terminology. I mean, I thought that on complex space it should be called Hermitian. Yes, and probably I write that beta and beta is 1 over absolute value of mu squared minus 1 q of bb, beta beta. So now, so our goal is to show. So we have our neuron-Severi space, and we have two forms here. We have the intersection form and this form Q. For the form Q, we know that it is non-negative, and the signature of the form of the intersection form is 1 and rho minus 1. And our goal is to show that in case we have such two eigenvalues, we get a contradiction with this assumption. So what I want to compute is product of square of alpha under intersection form times square of beta minus alpha beta absolute value squared. So just we write coefficients of our Hermitian form and yeah, so here let me mention that intersection form of alpha with alpha by this formula should be non-negative. So consider the restriction our intersection form to the space alpha beta, and our goal is to show that let me write it here. Goal show that intersection form restricted to space generated by alpha and beta is non-negative. This will contradict Hodge-Index theorem. How do we show it? We just compute the discriminant determinant of the restriction of Hermitian form to the space alpha beta. This is exactly minus alpha beta absolute value squared. This equals, by these formulas, this is 1 over absolute value of lambda squared minus 1, 1 over absolute value mu squared minus 1 times q of alpha alpha q of beta beta minus 1 over lambda mu bar minus 1 absolute value squared q of alpha beta absolute value squared. Then, first of all, observe that q of alpha alpha times q of beta beta minus absolute value of q of alpha beta squared is greater than 0. So we have such an equality. It is just Cauchy-Bunyakovsky for the quadratic, for the Hermitian, non-negative Hermitian form Q. So greater or equal. And also one can easily see that lambda squared minus 1 times mu squared minus 1 is, so we just can write it, but I don't want to. Okay, it is less than or equal to 1 lambda mu bar minus 1 absolute value squared. So this is just Cauchy-Bunyakovsky for complex numbers, if you rewrite it several times. So this implies that this difference is non-negative. And this contradicts Hodge index theorem for the intersection form. That shows that there exists at most one eigenvalue of the action of pullback on Néron-Sévère space of X whose absolute value is greater than 1. So all conjugates should be inside the unit disk. So we get theorem. That's it.
Can you repeat the last one? So how this contradiction says that
just if we have two eigenvalues of the action of pullback whose absolute value is greater than 1, then we get a contradiction. So we have at most one, and one and d1 is one is an eigenvalue of absolute value greater than 1. So it is unique, and all its Galois conjugates are strictly less than 1. Ну, для следствия, в смысле, лемма.
Явный вид вот Q, он как бы особо не пригодился, кажется. Вот когда мы доказывали всю эту штуку, нам явно не нужно.
Ну, не пригодился, просто...
Я понял.
Да. Это вопрос краткости обозначений. Окей. Была бы. Ну вот.
Тогда у нас же куба, ну, а там получается модуль альфа в квадрате меньше единицы. Ну это же ничего не противоречит.
Ну да, там. Okay. So yes, corollary from this theorem. So one more time, F is a birational automorphism of a surface. X d1 of F is greater than 1. Then one can show. And so let me. So in fact, this theorem is even gives. So here we can prove even more. We can prove that the dynamical degree d1 is a simple eigenvalue of action of pullback on algebraically stable, on Néron-Severi group of algebraically stable model. So there exists a unique up to multiplication by a positive constant nef class theta inside nef of x such that pullback of theta equals, so let me call it lambda theta. Then, first of all, theta squared equals 0 only if theta times e equals 0 for all e inside exceptional locus of f minus 1. And second, if theta equals 0, theta squared, then we can, so let us assume that f is algebraically stable. If theta squared equals 0, then there exists regular birational morphism, so composition of several blowdowns to S, such that here we have f, x, s, such that here we have a regular automorphism of S. G is inside. So we have we can birationally conjugate f to a regular automorphism of a surface.
Yeah, so in the theorem, we assume that d1 of f is greater than 1. Is there some birational morphism that it's for this not true?
For instance, identity. So there are many of them. For example, any automorphism of P2, regular automorphism, is such automorphism. Yeah, so this property is very easy. It is also from that formula. So 0 equals lambda squared theta squared equals pullback of theta intersected with pullback of theta. Yeah, theta squared is just theta intersected with theta equals theta intersected with theta plus sum of theta e squared. So we if theta squared equals 0, then we get that this sum equals 0. So each summand equals 0. So this is easy. Now how to prove this? So theta squared equals 0. So theta intersects by 0 with all exceptional divisors for f minus 1. So space generated by exceptional divisors in exceptional locus of f minus 1 lies inside theta orthogonal. And the intersection form restricted to the space, restricted to theta orthogonal, has so it is non-positive, and its kernel is exactly the line generated by theta. So if we can show that some e from here doesn't lie inside this kernel, is not proportional to theta, then by Grauert-Mühlich we can contract this exceptional divisor. So this, yes, exceptional divisor for f minus 1, and then we repeat this process and get the result. So let me show that theta is not proportional to E.
Can you clarify this form on that
Because theta squared equals 0. So we assumed that theta squared equals 0. Yes. So we consider theta orthogonal. Assume it contains a vector v such that v intersected with v is positive. Then we also know that v intersected with theta equals 0. And theta intersected with theta equals 0. So we get a two-dimensional space where the form is non-negative. And this contradicts Hodgkin's theorem. Какая теорема? Извини. Мюллиха. Да. Грауэрт, Артин, забыла. Да, извините, я что-то путаю имена.
Есть набор кривых, на которых форма причины отрицательная.
Вот, но тут мы будем все-таки по одной их стягивать, проверять, что внизу гладкое и что все остается прежним. Окей. Почему why theta is not proportional to E? Because if theta equals E, then so we know that pullback of E equals lambda E. So when we restrict pullback to the line generated by E, we observe that just on neuron-Severe lattice we don't have an isomorphism. Not automorphism, not invertible. Just because we the only automorphism of z is plus or minus 1. So theta is not proportional, so the form restricts to E negatively, so we can contract one E, and then we should check that on a new model, so the new model will be smooth, so this E will be among this E, we can there is a -1 curve, in fact, and that we will have the same property, theta squared equals 0 on the pull down. So this is not a complete proof, but the idea. So why do we need this corollary? Because it implies the following very nice theorem. So we know that, so theorem by Blanc and Cantat. We know that if f is a regular automorphism of a surface with whose dynamical degree is greater than 1, then the dynamical degree is either Salem or quadratic. So in fact, the inverse is almost true. So if f inside birational automorphisms of a surface X and d1 of f is inside the set of Salem numbers, then f is regularizable. Then there exists the regularization model, so a birational map alpha to y, a regular automorphism G of y such that the diagram compute.
Okay, can you repeat why? So how we get the contradiction with that is equal to E?
How do we get contradiction here? Just if theta equals E, then so E is eigenvector. So we can consider, so pullback preserves the sublattice generated by E. Then, but this sublattice is isomorphic to Z. The only automorphism of Z is multiplication by 1 or minus 1. So lambda should be 1 or minus 1, but we know that lambda is greater than 1. Yeah, so let us prove this theorem.
Sorry, I have a question. So in this corollary, what if this theta square is positive? Which sense is somehow like ample divisor. Then
So if f is algebraically stable and theta is non-zero, then f is non-regularizable.
sorry,
I mean, I think in this assumption we have an equivalence here.
so can we say something about this f itself? I mean, if we fix some with some ample divisor. Go back, theta is lambda theta, with this theta being ample.
We have dynamical degree greater than 1.
Yeah,
sorry.
So my meaning is, so in this case, can we always obtain this theta square is equal to 0?
Yeah, so if f is regular, then theta squared is automatically 0, yes. I just, sorry, I'm stupid, I don't listen.
I was wondering if there any correlation for this birational automorphism with which fix an ample divisor. I mean, this theta being ample.
But
just the big.
if
for the first case and the second
you mean if we have algebraically stable
yes,
automorphism which preserves
with theta square positive.
So if theta squared is positive, then it is not regularizable. So so theta is nef. So if theta its square is non-zero, then there exists E which is intersected positively. It can be, so yeah, sorry.
In particular, we may have some confusion about P2, for instance, right? In P2, the current is just 1, so it definitely preserves some ample divisor up to multiplying by the dynamical degree. And so what does this tell us about P2?
This tells us that if we have an algebraically stable automorphism on P2, then it is non-regularizable.
I guess, I'm not sure, maybe I'm wrong, but in this case, I guess all the eigenvalues has to be lambda. I don't know.
How is it possible? We just proved the theorem that
Because I think it fixes an interior point of this left cone, and with this coefficient lambda. Yeah, I just curious what's the situation.
Okay, yeah. Is it possible to fix? Yeah, okay. On P2 we fix an ample class, but it gives us nothing. So it is non-regularizable. It is very bad. And sorry, probably I just don't understand. Okay. what do I want to? Yeah, I want to prove this theorem that if dynamical degree is Salem, then the automorphism is regularizable. How do we do this? Let K be the field of the splitting field for lambda. So this equals lambda. Okay, splitting for lambda. Then there exists an element in Galois group of K over Q such that sigma of lambda equals alpha and absolute value of alpha equals 1 by definition of Salem number. So Salem number is such algebraic integers such that it is here and one of Galois conjugate lie inside D1. And then yes, yes.
I think we should name it somewhere. You need to name alpha to.
Alpha is just a Galois conjugate.
Yeah,
of
then there alpha.
Yes. Okay. Sorry. Yes, you are right. Thank you. Mu. Okay, we have an equality pullback of theta equals lambda theta. We apply sigma to this equality. So f is defined over z, so we get the following pullback of, oh, sorry. I'm just very stupid. It is not beta.
You tensor.
Yeah. I'm just.
Neuron severe group is C, or with K at least.
Yes, absolute value of mu. Sorry, I'm just Greek letters are very difficult, and I just can't. So we apply. So let us denote by psi sigma of theta. Just theta is a class in Néron-Severi space. We can apply sigma and get another class. So pullback of psi equals mu psi. We just applied sigma to this equality. Now we we use our formula about the product of pullbacks. So we know that self-intersection of psi equals, so it is mu bar.
I'm not sure exactly what this means. So do you mean the semi-linear action of the Galois group on the variety, or do you mean that you tensor the Néron-Severi group with K?
I tensor the Néron-Severi group with K.
Okay.
Yes. This is absolute value of mu equals 1, so this is equality. This is equal to self-intersection of pullback psi with itself. This is psi intersected with psi plus sum of e psi squared by all e inside exceptional locus of f minus 1. So we get that this sum equals 0. Then we apply sigma minus 1 to this formula. So this implies that e times psi, so probably it is absolute value because it is Hermitian form. Intersection of e and psi equals 0 for all e inside exceptional locus of f minus 1. We apply to this sigma and get that the same is true for theta. Then we apply this corollary and deduce that f is regularizable.
But this corollary works for when lambda is greater than 1. But we didn't use it.
So if it is Salem, then it is automatically greater than 1.
Yeah, but there we use that theta is an eigenvector with eigenvalue greater than 1. Or we didn't use it.
Yes, here everywhere we should assume that f is algebraically stable, of course. So otherwise, so here I write pullback of theta equals lambda theta. In this place, I just have already switched to algebraically stable model because on a random model we just don't have this class theta.
Yeah, that's I understand, but мы меняем фита на пси, и пси теперь это вот наш главный, вот как наш главный класс, который мы рассматриваем. Вот в королларе у нас тета это какой-то.
Ну вот я вернулась к нему. Я вернулась к нему просто применив к вот этой формуле сигма в минус первый.
Вот да. Что там? Почему сигма в минус первый на е действует? На
А потому что е целый дивизор. Е это кривая, она определена.
Ну да, точно.
Мы взяли элемент группы Галуа, который один корень переводит в другой, который по модулю равен единице. Перевели класс тета этим преобразованием в какой-то другой класс группы нейрона Севери. Применили формулу и поняли, что вот этот новый класс пересекается с каждым исключительным дивизором для f обратного по нулю. Да, а дальше мы используем corollary. Okay, so how many time do I have? Okay, I will be very fast and won't give you any more proofs. Черт, вот. Okay, so theorem by Macmullen. Sorry. So X is a surface, F is a birational automorphism of a surface, and lambda equals d1 of F is greater than 1. Then lambda is greater than lambda L, the linear number which we defined on the first lecture. So there is a gap in dynamical degrees. There is an interval between 1 and lambda L where we don't have any dynamical degree of a surface. So idea of proof. So let me give some plan.
You said that you know exactly the minimum of this lambda.
Yes. So there is a birational automorphism of P2 whose dynamical degree is lambda L, and there is also an automorphism of K3 with yes of K3.
To give an example.
No.
And do you know?
Yes. Yeah. Okay. So the idea of proof. We know that lambda lies inside the union of S and P. If lambda inside P, then if it is a Pizon number, we know the minimum of set of Pizon numbers, then lambda greater or equal than 132 and something. So lambda is inside set of Salem numbers. Then F is regularizable. We can assume that F is inside the group of automorphisms of X, and X is a surface. So in fact, here I said a surface, so this theorem works for any surface, but there are several types of surfaces where we can have a dynamical degree greater than 1. So these surfaces are either rational or K3 or Enriquez or abelian. If X is K3 or abelian or Enriquez, then F is regularized on the minimal model of the surfaces. If X, K3, Enriquez or abelian, then lambda, then rho of X is less than or equal to 19, 20, something. Okay, strictly less than 22. It is dimension of H1 20. 20, yes. Okay, and so the degree of minimal polynomial of lambda is at most 20. And there is some work by some guys who computed all Salem numbers up to degree 44. So then lambda is greater or equal than lambda L. The degree of lambda L is 10.
Are they finite in every degree?
Are they what?
Finite in every degree?
It is a good question. I'm not sure. As far as I remember, for degree 4, there was 2 inequalities on coefficients. It was something like minus 2 Q1 minus 1 Q1 minus 1 plus 1. And probably it gives only finitely many polynomials. So probably yes, and I saw a table where it looks like there are only finitely many in lower degree. Ладно, хорошо, не уверена. Но в любом случае они доказали это неравенство. So X is rational. And F is a automorphism of a rational surface. Then Picard number of X, so X rational. So one can easily check that if X is rational and it admits a regular automorphism whose dynamical degree is greater than 1, then Picard number of X is greater than 2. So then there exists a blow-up model of X. There exists delta from X to P2 such that delta is blow-up of several points on P2. Composition of blow-ups. Then we can, there is Nagata theorem. So yes, probably I we can consider neuron severe group of X. It is isomorphic to Z1n. This Z1n is the same thing as R. So it is a lattice with a hyperbolic form. So here we have a basis E0, En, and we can choose this. So this is called marking. A0 goes to the class of hyperplane section. Ei goes to the class of eth exceptional divisor. Yes, and so we can look at this space, and here we have an action of Weyl group. Weyl group is generated by reflections alpha, so reflections as alpha, where alpha squared equals -2, and as alpha of x is x minus 2 alpha x. So if we have an automorphism of x, f, then we get this pullback map. Here we have also the same marking.
Yes, this marking is isomorphism. Yeah?
Yes, isomorphism, yes. Yes, and there is Nagata theorem, alpha times alpha. There is Nagata theorem which says that in fact there exists, so Nagata, there exists element in Weyl group such that this diagram is commutative. So any inverse image map is induced by composition of several reflections. That there exists W in Wn such that the diagram commutes. Yes. So the question about dynamical degrees of rational surfaces reduced to the question of spectral radius of elements in Weyl group. And Macmullen just proved that the minimal spectral radius of an element of Weyl group is lambda L.
But it's a kind of non-traditional Weyl group, right? It's not a finite Weyl group.
Yes, it is infinite. So when n is equals 9 or greater, then this group is infinite, and starting with n equals 10, it has elements with whose spectral radius are greater than 1. And so
once again, here the main step was that we found a regular model for.
We found a regular model.
And how did we find the regular model?
Because it is a Salem number. So if it's Pizzo number, then it's okay. If Salem number, then we have these theorems.
And do we have a similar theorem for just a moment. So what's the beginning of the proof? Lambda equal p, then lambda is greater than 132 because all numbers in p are greater than 132.
Yes. Yes.
And this is by coincidence larger
by
than
Smith theorem, yes, by something. There are also some algorithms of constructing small Pizzo numbers which give the same result. So there are many proofs, but all of them are difficult. Да. Да. Да, да. Ага. Ну, чтобы свести все к Вейлю, то есть такая сравнительная свобода.
там идет дальше.
А дальше мы просто считаем, дальше Макмуллин просто считает все для группы Вейля. Это уже теория представлений. То есть, извините, я все равно добываю творог из вареников. Я свела одну теорему к другой теореме. Но математика, в общем, этим занимается, да. Вот, окей. I also want, how many time do I have?
20 minutes. Maybe a very small question. Can you remind, so Lemur number is the smallest known Salem number. We don't know if there is something less than Lemur number, but we know that there is some gap next to 1, so maybe Lemur number is not the smallest, but
Yes.
there is some generalized Lemur number which is still greater than 1. And do we know a similar theorem for Pizo?
Yeah, we know that this
Like 132
Is
border.
yes,
So
yes,
we know the actual border for
Yes.
Pizo numbers, unlike Salem numbers.
yes. In fact, I'm not sure that we know a birational automorphism with such dynamical degree. No, I just don't know, but it should be known. Yeah, okay.
Yeah.
Yes, I don't know. Yeah. So okay. So next theorem is.
I'm sorry, what about X, which is the general type, and
But you could find it more from
Yes, a finite automorphism group. So yes, this is also a theorem. If we have a birational automorphism of a surface whose dynamical degree is greater than 1, then X is either rational surface or it is birational to K3 and or abelian. Okay, so
the strategy of getting the cottage cheese from dumplings, it can be proved using this Diller-Favre characterization of. If we believe that any automorphism which preserves an elliptic operation vibration has degree 1, and this part of Diller-Favre theorem is simple, right? If it
Yes.
preserves, then
Yes.
the degree
Yes.
equals 1. Then for genotype there's nothing to prove. For cadaveric dimension 1,
it is also easy because we have another vibration.
and then it just takes along the vibration and there's nothing on the base. And for
The elliptic we have Albanese.
and for non-rational
Yes,
ruled surface we have
also a vibration.
vibration problem.
Yes. And in fact, the proof is just the proof, yes. So now I want to talk about lambda of x, or just lambda, sorry. Lambda is the set of lambda 1 of f, d1 of f, where f is a birational automorphism of x. X is a surface, and yes, and d1 of f is greater than 1. So such another subset of R. We had subset S and P. This is a new subset which intersects, which lies in their union, and we don't know many things about this set. So a theorem which is nice also by Blanc and Cantat. The set of lambda is well ordered. So any subset of lambda has its minimal element, and also lambda.
Different lectures from the same school have to have something common.
Yes. Lambda is closed. Lambda intersected with P lies inside lambda intersected with S closure. So this is just the same, the analogs of assertions we proved on the first lecture but just the part which arises in geometry. We proved that Pizot numbers lie in closure of Salem numbers, and in fact, Pizot number, which is a dynamical degree, also lies in the limit of is a limit point of the set of Salem numbers, which are dynamical degrees. Complement. Yes. So let me recall. P. So U is set of lambda greater than 1, such that they are algebraic integers and all conjugates are inside D1. P, closure of D1, is the same thing, but all conjugates lie inside, strictly inside D1, and S is a complement. Sorry?
Меня смущало то, что они вроде как дополнение друг друга, так что они не должны лежать, но потом
замыкание, да. Да-да-да, я говорю, что каждому сходится последовательность. Okay, why this? So I just want to answer questions you asked me previous times. First of all, so what corollaries do we have? So corollary. If lambda is inside lambda, then there exists epsilon such that lambda intersected with lambda plus epsilon is empty. And now we have lambda g, golden section, 1 plus square root of 5 divided by 2. This is a Pizot number, and there exists a sequence of Pizot number such that which are greater than lambda g, so decreasing sequence. Such that its limit is lambda g. So infinitely many of these Pizot numbers are not don't lie in lambda. So there are infinitely many Pizot numbers which don't which can't be realized as dynamical degree. And also we know that P is a closure of S. So for each of these Ti, we have a sequence of Salem numbers which converges to theta I. And so we also have infinitely many numbers, Salem numbers, which also can't be realized as dynamical degrees. So this set contains some, but not all of dynamical degrees, not all of Salem and Pizot numbers. Still, this set is quite big. So we know that lambda is ordinal, and it is computed. So there is theorem by Anna Katarina Bot, which says that lambda is omega to power omega. So we have infinitely many sequences, sequences of these dynamical degrees. Now,
здесь вот в этой теореме в определении лямбда f пробегает персональные математические исоморфизмы поверхности, да?
Поверхностей, да.
Да. То есть я так понимаю, что вообще, если брать не поверхность, а любую размерность, то все-таки вроде как я нашел, что любое число Салема там представляется, реализуется в таком виде.
Да, окей, давайте я напишу эту теорему. Я не знаю. Ну да. То есть утверждается следующее, что это называется теорема Суджимото. Which says that if lambda is inside the set of Salem numbers, and then there exists simple abelian variety A and its automorphism F. Yeah.
F,
Such that d1 of F equals lambda. Moreover, one can consider the set of all dynamical degrees of F, where F is inside automorphism of A, where A is simple abelian variety of degree of dimension which is equal to G. So then this set contains its minimum.
and G fixed, yeah?
G is fixed, yes, for fixed G. And but if we don't fix G and consider all dynamical degree of F of automorphisms for all simple abelian varieties, then this set doesn't have minimal value.
It has minimal value, but it's not a linear number.
Yeah, so it could be less than lambda L because lambda L is realized on some abelian variety, probably.
Because what you say implies that not only certain numbers, but many other things are realized as these degrees because. Sorry? No, that's right.
So yeah, so this set contains S, but it contains something else. So it says nothing about minimal root of minimal Salem number. It probably says something about, so it doesn't answer Lemierre question because we just know that, I mean,
this
it's
minimum, it doesn't have minimal value, but consider its infimum. Is it 1 or greater than 1?
Yeah,
the
I suppose you should say that d1 of f is greater than 1.
d1 of f is greater than 1, yes.
Yeah, but the infimum of a set of numbers which is greater than 1, yeah, of course, it may be 1 or greater than 1.
Yeah, it has minimal value that greater than 1.
But here it does not have.
Yeah,
So probably it is separated from 1, probably not. And the question is still not answered.
Is this Sugimoto an old theorem? Is this Sugimoto old theorem or?
23, yes.
Very new.
Yeah.
Yeah, it's the second part. The first thing, is it contain the Salem numbers?
It contains all Salem numbers by the first point.
The first one, where we fix dimension of a Abelian variety. But first,
it does not contain all Salem numbers because it contains, so I mean here the Picard number of such A is bounded. So the degree of D1 is bounded. So yes. Okay, so probably I have 10 minutes.
Maybe 5, but
5.
10.
So yeah, okay. Then I want to prove this fact because I just like the proof. Yeah. Yeah. So in order to prove this, so what do we want to prove? We have a sequence of elements in lambda. Lambda 1, lambda 2, lambda n. We can assume that this sequence is decreasing. So strictly decreasing. Probably not strictly. And we want to show that it stabilizes at some point. And we know that lambda 1, lambda I, equals to dynamical degree d1 of fi, where fi is some, so this theorem also stated for all surfaces, but in fact it is interesting only for P2, because if so if some fi here are automorphisms of K3 surface or Enriquez surface or abelian, then the degree of lambda of its dynamical degree is bounded by 22, and the set of algebraic numbers of whose degree is at most 22 is discrete. So we can assume that fi lies in the group of birational automorphisms of P2. And then we use a very difficult theorem, also proved, so yes, obviously proved by Blanc and Cantat, and which says that if f is a birational automorphism of P2, and lambda 1 of d1 of f is greater than 1 million, then minimum by all g inside Beer of P2, degree of the conjugate automorphism g f g minus 1 is less than 4,700 lambda d1 of f to power 5. So if dynamical degree is very big, then we can bound the degree of the map. We can conjugate it to a map of sufficiently small degree. It is a very difficult theorem. So it takes, I don't know, 20 pages. Ну, если хочешь, посчитай их алгоритм и сделай это, но мне кажется, что это довольно гадко. Ну, в общем, я не знаю. У них алгоритм, то есть, нет, там правда сложно. Там, для миллиона. Да, у них теорема, ну, может быть, там какие-то более точные числа, но, в общем, я не стала это читать. Это они сами доказали. Вот. How can we use it? So we have this sequence. It is decreasing, and yes, so we can assume that lambda is a limit of lambda n goes to infinity, and we can assume that lambda 1 is less than lambda plus 1, and this is greater than lambda. yes, and what is important, now we know that lambda is separated from 1. It is greater or equal than lambda L. So you can just check that lambda L to power 86 is greater than 1 million. So let me call this number m. There exists some m such that we have such an equality. Then we know that f d1 of f n to power m is greater than 1 million. Then fn to power m is conjugate to gn, which lies inside birational, whose degree of gn is less than or equal to than 4700 lambda plus 1 to power 5m. This, let me call this d. This is some integer, so probably we choose some 5m. Yeah, so 5 is from here, and m is because we take this power. So this is d1 of fn to power m, which is lambda n to power m, which is greater than this. Нет, они... сейчас, я перестала понимать, что вы спрашиваете.
Мне казалось, что d1 от f там, в какой-то степени не степень d1.
Нет, это если оно алгебраически, в самом деле, как Настя сказала, если оно алгебраически стабильно, то...
можно алгебраически стабильно.
Да, мы можем считать, что они все.
Алгебраически стабильным. Мы же типа взяли, зафиксировали, что у нас P2. Если мы хотим его сделать алгебраически стабильным, нам надо как-то P2 взять его рациональную модель какую-то.
Ну, мы fi, в смысле, я просто как бы утверждение, что d1 of f to power n equals d1 of f to power n follows from the existence of algebraically stable model. Just this is number which we compute for any birational automorphism. Yes. Yeah. So we choose some integer which is greater than this number, and this number don't depend on n. So we get that gn lies inside birational automorphisms of P2, which are given by homogeneous polynomials of degree at most d. So this is the notation for this subset.
What does it mean?
This means that gn is given by homogeneous polynomials whose degrees equals at most d. So for all n. And then we use theorem about semi-continuity, yes, semi-continuity theorem. Theorem by Xi, which says that if we have a family of surfaces x over t family, of surfaces, and we define birational automorphism in each on each fiber. So f is inside birational automorphisms of x, which are fiber-wise, so they preserve all fibers over T. Then lambda d1 of ft is lower semi-continuous. So here we have such situation. So this BIR D is, on the one hand, it is just a variety. It is correct. So it is algebraic variety. In particular, it is Noetherian. And on the other hand, it defines family of birational automorphisms of P2. So we just consider BIR D times P2, and over each point here, we just consider the birational automorphism. So it is the topological family. So we know that dynamical degrees in this family are lower semi-continuous. So what means lower semi-continuous? It is exactly means that the set of all T inside T such that lambda 1 of ft less than lambda than something then mu less than or equal to less, strictly less, is closed. So then we look at this sequence and observe that each strict inequality so this is T mu. Then we have T lambda 1 is closed. This is just the statement of this theorem. So T lambda 1 contains T lambda 2, contains etc. And all these inclusions are proper. So at some point this sequence should stabilize because we are on an algebraic variety. We don't have an infinitely long sequence of embedded subsets. So then this sequence has its minimal element. And I think I will stop here.
Any questions about degrees?
So you had a statement that lambda intersects with Pizon numbers is includes in the closure of Salem intersect with lambda. But do we have inclusion in another way? Like, is it equal actually?
No, because so we have lambda L, which is separated from Pizon numbers.
Ah, yeah, because it's separated from its limit. Okay. And another question: do we know anything about other varieties except that abelian? I mean, this theorem is about abelian, but maybe we know something about Fana variety or whatever.
So for Fana variety, so if we are talking about greater dimension, yes, it is very difficult, and there are some results, but not very nice.
Do you at least know what these numbers algebraic?
I don't know.
What? Sorry?
Do you know what these numbers algebraic in higher dimensions?
The dynamical degrees could be transcendental in higher dimensions. So yes, yes, and they are very difficult. Давай потом.
And so we don't know any well-orderness. Well, after all, they may be transcendental, but still there's a chance that they're well-ordered.
Yes, but so here they use, for instance, this assertion, which which was very difficult to prove in dimension 2. I mean, probably yes, but it is. Yeah, and also I just want to say that Salem numbers are not well ordered, as we know, because we have a sequence which converges to the golden section.
Yeah,
and
but,
so
but,
this.
but of course, if we don't bound the dimension until we take all of them, then there's no hope for any kind of hollowness. It's a usual thing. But of course, we fix the dimension, say 3.
I don't know. No.
But this same continuity holds in
Yes.
as well,
Yes.
right?
Yes.
So there is some hope.
There are. Yes.
By the way, as I understand, all of these look for any characteristic.
So most of these assertions work for characteristic 0, but algebraically closed field, not only for C. So, for instance, the fact that the set lambda is closed is not true. So is not proved in finite. So for non-countable fields, as far as I know. Yeah, so it is difficult to generalize.
Other questions?
Yeah, you said that for this lambda, big lambda, as I said, we have some epsilon that if we have some small lambda in big lambda, we doesn't intersect, the big lambda doesn't intersect with lambda and lambda plus epsilon. So some, do we know this epsilon? Or it's just
No. I don't know if it is known a concrete Pizzo number which is not realized by as a dynamical degree. So. Yeah.
Okay, let's thank Sasha again.